Thank you for the nice introduction. How's everyone doing today? Um, so right now is probably the most interesting time that I have witnessed in my career in terms of natural language processing, but even AI in general. This extends across all domains, but for today I will focus on the domain of finance, being that's where I work and where there are some interesting case studies to follow. So before we dive in, I just want to give this little bit of a perspective in terms of the timeline of natural language processing and how quickly things have gotten to shift. So natural language processing was the field that probably came into most prominence early on in investment management. So, back in the 90s or the early 2000s, finance was sort of the first to the party to start digitizing news or digitizing company disclosures. And people would build these financial sentiment companies where you would maintain these long vocabularies of words to say, bullish is good for financial sentiment and bearish is bad. And from these big vocabularies, they would build these sort of handcrafted models for things like sentiment. And of course, things have gone a long way since. In 2013, the first forays into deep learning for natural language processing have started. We figured out that we could create word embeddings to start representing language as numbers. First in small words like blocks, and that was really the building block to then figure out, okay, well, we could now construct these recurrent networks or long segments from these word vectors stacked into essentially a long matrix that we can then architect networks that were built with the sequential structure of language in mind to try to do things like machine translation. From machine translation, the self-attention mechanism was born in 2017, where we realized that there were better architectures called transformers to do natural language processing. And then pretty quickly in 2018, the BERT model came around. This around the time where I myself have started getting really heavily involved in natural language processing because BERT was the first language model. It opened up the ability for us to model language and do things like sentiment, like detecting topics, like detecting named entities in more sophisticated ways. And we'll talk a little bit about that. In the last 5 years, things have improved very quickly, but November last year was a big and very visible step change with large language models very rapidly becoming very, very good at, well, a whole lot of stuff. And we'll talk about the ones that are most relevant to the field of finance. This growth in large language models, the improvements, can be attributed to sort of the same three common factors we often hear about in terms of growth in AI in general, right? So advances in machine learning and open source tool sets, our better architectural understanding of how to build language models has allowed us specifically to scale models to be very large. Combined with the growth of data, the data question for natural language processing and for large language models specifically is actually a very interesting one because it's partially that we do have more data, but it's more so that we figured out of how to extract knowledge basically from all the language that we have written down to date. So we'll talk a little bit about that as well. Interestingly enough, one of the limiting factors today for how good large language models are probably going to get, at least one of the scaling dimensions, is how much data we have. So we're literally limited by the amount of stuff we have written down over the years and put on the internet. There's a little bit of irony in that, I think, if it sort of leads to general intelligence, because we all just have been making training data our whole lives, no matter what kind of writing we do. But nevertheless, and the last one is advancements in hardware, optimization, making predictions cheaper. This one is also an interesting one because with the advent of large language models, we are probably for the first time at a place where we are truly compute constrained for machine learning. And I say that in the sense that we've had, of course, a ton of machine learning workflows running in a lot of data centers, but a lot of the models that we've built historically have been arguably frivolous in terms of computational resources, at least in certain places. But with large language models, we are starting to see a very, very clear exchange rate between some kinds of human cognition and work that we can switch onto a computational workload in a much more general sense than before, and the computational cost that these models run into. And so basically what this means is that the demand for these models has grown so quickly that even OpenAI, for example, is very heavily constrained by lack of GPUs in terms of giving demand to companies that are trying to use these tools in terms of advancing their own internal roadmap. So we're hitting a much more profound point of computational constraints than we had in the past. And that's because that exchange rate has shifted. The value that we can build using AI is higher than it was ever before, in a way where we really are, running against just not having enough GPUs, period. So that's very interesting. So let's talk about how we got there. So to understand what's changing in NLP specifically for the kind of stuff that me and my company and my research is based on in investment management, it's good to start with 2018, with the BERT model, the first language model that came out. The idea, there were two core ideas behind BERT. One was the transformer architecture, the word that you've probably all heard, the type of neural network that just turned out to be better and scalable for building large networks for natural language processing. And this really interesting idea of language modeling or pre-training. The way BERT did it is basically play fill in the blank. So if any of you guys have ever done a language test, you might have had a question that is like, the blank jump over the fence. And as a human, because you have a good understanding of language and a good world model, you know that the anvil jumped over the fence is a very unlikely answer because the anvil can't jump. And the dog jumped over the fence or the sheep jumped over the fence is a reasonable answer. The sheep, maybe being more likely because of sheep counting and what have you, right? So these are all things that we sort of have a good intuition for. But it turns out that training networks with these sorts of tasks, with these kind of fill in the blank type games, made for a really, really good baseline that we could use as a launching pad to do a lot of other things. And the utility of the BERT model wasn't in this pre-training itself, that it got good at playing fill in the blanks, or that it got good at another game it played, next sentence prediction. It does one sentence logically follow another. But the fact that we could basically take this model and hack it to do the 4 or so tasks that were most common in natural language processing, and have, in their own ways, have a lot of different applications. The tasks basically would be named entity recognition. So can we recognize companies or locations or people? Can we do similar tasks that maybe aren't named entities, but we want to detect something else in a piece of text, like the answer to a question? Or they could be sentence level or paragraph level tasks like topic modeling. Is this talking about earnings for the company in a positive or a negative way, for example? So, and this suite of tasks we got pretty good at, but when it came to solving problems with BERT, we had a really, really big bottleneck, which was actually humans. In order to build models to do these specific tasks and to do it well, we needed to go through a process called fine-tuning. So we had to curate a bunch of human examples that says, okay, here is 500 examples of this given topic, and here's 500 examples of documents that I want to process that don't have this topic mentioned. And based on that, we could fine-tune a model. And surprisingly, even though BERT was a really large model for its time, the amount of data required to fine-tune it to do these specific tasks was lower than trying to build a model to do them from scratch. So it really improved the economics of natural language processing and opened up the aperture to allow us to do more things in NLP with a better user experience, with lower investment, and really opened up how well we could design a product. Next come large language models. So since BERT came around, there was a slow trend in the background of scaling up models to be larger and larger and larger. This idea of playing a game was replaced by, instead of filling the blanks, we would play next token prediction. And if you think about this next token or next word prediction game, essentially the idea is very similar to fill in the blanks. You take a piece of a sentence or a paragraph, you chop it off at some point, and you get the network to predict what the next word or token in the technical NLP language would be. When we play this game on basically the entire internet and see how large of a model we can scale to play this game, really, really interesting and surprising properties emerge. And this probably isn't so surprising for folks now, having heard everything that's happening with Chat GPT, having potentially used, the latest BARD or Palm-based models from Google or GPT-4. LLMs have gotten really, really good at what I would call propositional logic. And you could see this early on in the Palm paper from Google, right, where they had an example on the bottom right where this model has only learned to play the next token prediction game. But when you ask it a question like, Jennifer looked out her window and sees a really cool cloud below her, she unbuckles her seatbelt and heads to the bathroom, is Jennifer probably traveling more than 300 miles per hour relative to the Earth? So this is probably a question that the model never encountered before. As a human being, you can infer through logical reasoning that, okay, well, she unbuckled her seatbelt, she's looking out the window, there are the clouds, so she's probably on an airplane, and since the airplane is flying, she's traveling more than 300 miles per hour. The large language model can do the same. This was at the time, and possibly still is, the largest large language model that we could build. This was the Palm model by Google at 540 billion parameters. The interesting thing here is that basically this number, how many parameters a model has a very direct relationship with how much training data we have. So we developed kind of a better understanding over time of two things. So one is, all else being equal, if we can make a model larger in certain regimes, sort of when you have enough data, it starts, for those who know machine learning, there is the very common kind of concept of bias variance trade-off. The bias variance trade-off basically tells you that, as you scale a model size, you might start with the model that's too simple. That's on the far left in this chart, and this model is too simple, it's kind of dumb, it has a very high loss, it doesn't do very well. And as you scale it to be bigger, it gets more expressive, and then your loss goes down as your model becomes better. And then eventually your model becomes too big. You start overfitting or not generalizing well, and your loss starts going back up. So there on the left, that's just the bias variance trade-off. But in the past, we didn't have as many computational resources, and we haven't really thought about saying, okay, well, what happens if we make the model even larger and even larger still? And so it turns out that if you run those kinds of experiments in certain regimes and you make the model even larger, eventually there's an inflection point. And from overfitting or lack of generalization, you actually start getting to the point where your loss goes down. And it's a little hard to see on the chart, but the point is it basically goes down lower than that lowest point on the far left. So somehow we're able to sort of infinitely scale models, and seemingly we can't get infinite performance, but at least we get some sort of asymptotic performance where they don't get worse. They continue getting better. So this is one of the core ideas. And from studying this, there have been a ton of papers in the past 5 or so years that basically show that this holds up. So from the GPT-3 paper, from scaling the model to, from 1 to 175 billion parameters that GPT-3 had, the performance on these zero-shot benchmarks. Zero-shot benchmarks are basically, little questions where you say, here's a definition of a topic. Can you recognize this topic in a piece of text or not, right? These little questions that you can easily test. Without training data, without fine-tuning anymore like we had to do with BERT, we started getting better and better and better at the zero-shot benchmark. But on its own, even this wasn't super impressive. So we were able to scale these models, and they sort of got better, and they got measurably better at the zero-shot problems. But on its own, they still weren't quite usable. We understood a little bit more about how to scale them better. So in 2022 or so, we started getting a much better idea what the scaling laws of large language models were. And in fact, there it seemed, or looking at this in isolation, one might think that our ability to really improve on this dimension was kind of slowing down, because we sort of figured out that models like Palm or models like GPT-3 were undertrained rather. So basically, like, given a fixed compute budget, they were probably too big. We could make them smaller, maybe get them a little bit better, but they're also this sort of asymptotic behavior where we were maxing out our ability to play the next token prediction game. And from that, we weren't seeing enough improvements to make these large language models something that's very generally useful for business. However, here comes in the second part of making a very, very good large language models, which is fine-tuning our human alignment. The fine-tuning paradigm in large language models is a little bit different. So what OpenAI specifically did, And what allowed them to be the first to market with a large language model-based product that was really incredible is get really, really good at this alignment step. So they had, the same large language models that folks have with GPT-3. GPT-3 at this point was pretty old. And they collected a bunch of human feedback to basically give the model a thumbs up or a thumbs down when the outputs it was producing were good or bad. Together with pre-training that model using in the next token game, the results were really, really incredible, as a lot of us saw interacting with these tools. Better yet, when the GPT-4 model came out, this is where, and even for, I think, folks who are really, really deep into this stuff, for the practitioners, the results from GPT-4 in particular were very, very surprising. Because it turns out that as a combination of playing the next token prediction game plus really, really good alignment, we could make models that, for example, could pass the bar or pass the LSAT. And the LSAT for me is particularly interesting because, for those of you guys who maybe have seen the test, a lot of the LSAT questions are basically veiled IQ test questions. So they're just reading comprehension propositional logic questions. When Chat GPT came out, it was really, really bad at propositional logic. So if you asked it a puzzle, it would promptly fail. But when GPT-4 came out, and some of the models that are from other providers that are similarly advanced as GPT-4 is, this propositional logic question is basically cracked. And here you see the performances from GPT-4 on these different tests. By the way, an interesting thing, and something you have to keep in mind if you're benchmarking two different large language models, or if you read a claim saying, okay, this large language model does as good as the other one. Where you really see differences between these models is in more complicated tasks. So what OpenAI showed that, like, for simpler tests, ChatGPT and GPT-4 basically did the same, and they both did fine. But as you start scaling the task to be more and more complex, the difference between a sort of worse performing model and a better performing model becomes more apparent. So turns out it's quite difficult to benchmark models against one another, because you might just be trying one task where both models do fine and you haven't sort of found the breaking point where one gets better than another. In terms of alignment, the really interesting kind of question becomes, there's some interesting research to show that as we align models more and more and more, we can potentially hit some diminishing returns. So there is a really interesting video by Rob Miles on computer file and alignment, where I just pulled out one quote where he said, "Making buggy code are we?" The idea being that basically these models in certain cases might be a little bit too clever. And when we get a model to program, for example, a slightly sillier model might just write correct code, whereas a smarter model would say, well, this is a situation where a human would probably write buggy code. Because I'm really well aligned to do what a human would do, I will also produce buggy code on the spot. In terms of finance, however, I think it's really important for us to decouple these two sets of capabilities. So there's the propositional logic layer, right? So, models like GPT-4, these sufficiently advanced large language models, are basically propositional logic machine. So if you give it some data and you ask it to make a logical inference, it does as well as, let's say, an average human. It's not superhuman, it's not super intelligent. If you're clever, it's probably not more clever than you. But it can do these things at a large scale, and it can really shift away a lot of kinds of cognition that are just making logical inferences from one part of data to another. The other part of it is remembering stuff, right? So when we train a large language model, we get these, this ability to basically reason, at least to some degree, right? And you get it to remember stuff. And so if you interact with Chat GPT or something, right, it's always telling you, based on my knowledge cut off until 2021, I'm not really sure. I would argue that for a lot of products that, that we're going to be building and using, decoupling this logic ability from memory ability is really, really useful. Because what it means that, like, we already have really, really good algorithms to search, to serve up the right kind of information for this model. So when it comes, for example, to writing reports or for making label data for smaller models to run on a large scale, like we used to have to for BERT, now we can have large language models make this label data. When it comes to tasks like data mapping or basically almost anything that I can think of in terms of kind of data restructuring tasks, we probably already have the backbone to engineer any sort of analytical product that you could possibly imagine. but it still requires engineering. And sort of as one thinks about engineering these products, it's useful to think about, okay, is this a spot where I can use an LLM for memory, for its ability to remember facts, or if I can just use it for the propositional logic abilities that it provides. There's some interesting work that folks are starting to do. For example, there's a model called Okra that tries to do this, tries to distill the kind of logic reasoning abilities for models like GPT-4 separately from the fact-checking abilities, because it's possible that we end up using just one over the other, and we can save some computational resources from saving some of the memory. But nevertheless, this is basically jet fuel for building products in finance and in a lot of other domains. I'll give you guys a concrete example of this as well, so it's hopefully a little bit more clear. So here is it's going to be hard to read. I'll read it for you. On the left, I asked Chat GPT-4 a question about, so let's say hypothetically there is an earthquake in the Chennai region in India, which S&P 500 technology companies might be affected. And it says, well, I don't think any of them will be really affected. Maybe they have some services partners there, maybe this, that, or the other. But recently, I read an article that says that Apple is starting to produce iPhones in that region. So I can say, well, in the context of this article, do you think Apple might be impacted? And then it says, it sings a slightly different song, and it says, yes, well, of course. And these are, the considerations that you may have to think about in order to actually assess the risk level here. It's all pretty reasonable stuff, all quite sensible. Like if you asked a person in finance, they would probably give you a very similar answer. But the point is, it's based on information that the LLM doesn't really have. But it's very easy, well, or at least it's very well understood how to serve that specific information so that it gives us the right kind of response when prompted. And this general pattern is how a lot of engineering with these models can work. And the really, really hard part here is the logical inference part, right? Like these complex logical inferences are something that we couldn't really automate in the past, but at least that part is solved with the LLM for us. So it really does open up the design space. I'll end with this. So to me, this is very, I've had kind of versions of this slide over the years that talk about what is or isn't changing in the world of AI and natural language processing. And I used to always say that, okay, well, we're in the world of task-based AI, right? So no matter what, we need to set a loss function and a human needs to set a loss function for some algorithm that we're optimizing. And no matter what, we need the human element because we have a world model. We know things that aren't in the data. So if some feature is biased, we are the ones who can know that. That's changing now a little bit. So we have models that do have a world model. And we have models that aren't artificial general intelligence, but it's also very difficult to call them task-based as well. They do have that level of generality. But I think the optimistic part for me here, I'm realizing recently that the human element for building with these tools is possibly even stronger than before. So because, for example, for doing things like prompt engineering, having a really good understanding of how these models work and a really good business context for whatever problems that you're trying to solve can really, really move the needle in terms of generating better products and better outcomes. I'll leave a few minutes for Q&A. So for me, I have my own company. Responsibly, we do a lot of work in this. We're building with a lot of these tools for creating a better experience for investment research. And I do research as well at the University of Toronto with a lab called Risk Lab, again, working on a lot of these questions. What can we do with these models in finance now that we have models that have a world model? What happens to interpretability? What happens to causal analysis? And what happens for our ability to structure data and make the job of a human researcher better? And yeah, so I'll leave you guys with that. Hopefully you enjoyed the talk. Any questions, please?
I'm wondering if you had any, given that most data in finance are structured and time series, I'm wondering if you had any experience fine-tuning or developing a large language model that consumed that kind of data, and what do you see, challenges of consuming that type of data for language models?
Yeah, I mean, there's a couple parts to this, right? So most data consumed by asset managers, especially on the quantitative side, is time series data. But that's just because that's how they consume it, right? So a lot of it ultimately comes from unstructured or semi-structured sources that just ends up being delivered to them in that particular format. And one of the applications of large language models is just to do this in a much better way now, right? Where, for example, if you're working with text, historically, like sentiment signals are pretty unsophisticated, right? It's like, okay, well, does this company have, on average, positive or negative sentiment on this particular topic? But in fact, underneath that is a lot of different things are happening, right? And not all negative sentiment is the same in terms of impact on the company's earnings, for example. So now we have the opportunity to potentially create these signals with just, well, a lot more depth behind them than we could in the previous world of fine-tuning and BERT and stuff like that. In terms of serving or how NLP large language models interact with structured data, there's really two ways, right? So one is you use an LLM to structure some data and then feed that essentially as a feature in in a downstream model, right? Like in finance, this could be just a regular, logistic regression or tree-based method that takes in a bunch of time series, some of which can be produced by an LLM. And that has certain advantages. Specifically, what these models don't do a great job at is kind of probabilistic or Bayesian reasoning, right? So you can't use it on its own in lieu of other supervised learning techniques. Wouldn't do a great job at that, right? Like you definitely shouldn't use it on its own for like credit risk evaluation or something. But you can use it as an amazing feature engineering tool to make credit risk evaluation better. The other approach is you can turn some of your structured data unstructured to say, hey, here is some context, here is some structured data, can you make some logical inference to produce some other kind of structured output? That sort of pattern can be very, very useful as well, but it's kind of use case specific, right, which way you want to go. But definitely, it makes it easier to combine structured and unstructured data. You just have to be clever, and there's a few patterns for doing it effectively.
Thank you.
Hi, thanks. I really liked your talk. One of the things that we are all grappling with is, should we build our own large language model?
No.
Or not? It was a pretty short answer. Could you elaborate, some of the reasonings that underpin your answer and why?
Yeah, of course. I mean, it's expensive, right? So ultimately, it's a cost-benefit analysis. So you have a few options for deploying an LLM into your process. And the cost-benefit will vary depending on exactly what you're doing. But your options are basically train your own, fine-tune a model, or use a model without fine-tuning and do more work in prompt engineering. So use sub-searches to find relevant information to give into a prompt. Potentially, that can make every LLM call more expensive because your prompt becomes more expensive itself, right? So whether you're using an API or even you're running your own model, at the end of the day, like every single input is going to be more costly. However, with the next-gen models, you can basically, like, in my experience, get whatever performance I would dream of getting before with those types of patterns, right? Either fine-tuning or not even fine-tuning, just serving information and doing prompt engineering. So really training your own LLM is either you think you can do better than them for, like specifically for that part, for the propositional logic part, or it's really, really expensive, like you have to make a crap ton of calls and it just will end up cheaper for you to train your own, or you needed to remember some kind of data, and for whatever reason you can't serve that data up in the prompt, you really need the LLM to remember that data. But all of those just seem like very, very rare edge cases, right? So maybe there are spots where you do want to train your own, but I think for the most part, it's not economical to do so, right? For the vast majority of people, of companies.
Thank you.
Thank you for the presentation. This topic is about how AI or natural language processing can make use in the financial industry. Do you have an example or case how you leverage the natural language processing model and make some business decision, maybe have some dollar value there?
Yeah, ultimately it all comes down to time, right? So in the investment management industry, most strategies are still run by humans, right? So you have about 300,000 investment analysts globally on the buy side that consume a lot of research that's made, let's say, by sell-side firms or made by other providers in in ways that require a lot of humans, right? So there's a lot of human cognition that's basically shuffling kind of information around, be it on the sell side or other types of providers. And they themselves spend a lot of time in day-to-day making decisions, reading a lot of stuff still, and looking at a bunch of Excel files, so making valuation models that to help them make an investment decisions. All of this can now be ostensibly automated, right? So, or at least a very, very big part of their day. So it's not, I don't think it's so much about like a specific use case, and it's not unique to finance either, but just in any knowledge-based industry where people are essentially distilling information as their job, like you read some stuff and you condense it into a shorter version through an email, through a PowerPoint deck, through an Excel model for someone more senior to help them make a decision. And that's a lot of hours in our economy, right? Like all of those jobs are going to change or shrink. Investment management is just a subset of that, but just the same applies. It's just that we have now the tools to shift a lot of that cognition from humans to algorithms.
Thank you.
Thank you. Thanks, everyone. Thank you for coming.